you look at a word problem. Okay, you just let me know. So we're given a cost function which is 2000 x squared plus 2 raised to 1/3 again and plus 700, where C of x is the total cost in thousands of dollars. Thousands of dollars of producing X units. Fine. Find the rate at which total cost is changing when 20 are produced. Find the rate of change of cost when 20 are produced. So in order to find the rate of change, what do I have to find? We have to find C prime. So 2000 multiplied by 1/3 is 2000 over 3. X squared plus 2. I subtract 1 from 1/3, so negative 2/3, times the inner function prime, which is 2x, and plus 700 prime, which is 0. So this function is 4000 x squared plus 2 to negative 2/3, everything divided by 3. So now I'm asked to find C prime of 20. And I will plug it in. Where's my calculator? Here. Be very careful how you plug it in. In this case, because the denominator is just one term, it's okay with parentheses around the numerator or without, but be careful otherwise. So 4000 multiplied by 20, because x is 20, open parenthesis, so 400, because 20 squared is 400, plus 2, close the parenthesis, put a caret, in parentheses, negative 2/3, close the parenthesis, come down from the power and divide by 3. And press enter. So I got 489.57. 489.57. And tell me what is the measurement unit for this? The rate of change of dollars per unit. Without the chain rule, we would have not known how to differentiate this function.
Okay, so that so we don't do anything with the 700, is that right? Plus 700.
The rate of change of a constant is 0. If it had x in here, it would have been plus 700, but it doesn't, and the rate of change of this of 700 is 0.
And then, where did you get the 2x from? Was it from the x squared?
Yes. So I brought down 1/3. I subtracted 1 from 1/3, and then I had to differentiate the inner function, and I got 2x. Okay, let's look at another. Let's say a compound interest. The formula for compound interest is, you may remember it from algebra. Okay, what is all this? This is the accumulated value. This is the principal. This is time in years. This is n. N is the number of times the interest is recalculated. We say compounded. Number of times per year. The number of times per year interest is compounded. R, annual interest rate. Okay, so we're given this time A equals 1,000, 1 plus R over 4 raised to 20. And we're asked to find the rate of change of A with respect to time. With respect to the rate, sorry. So we're asked to find, that's the variable. So this should be A of R. So we're asked to find A prime of R, which is the same thing with dA over dR. We use these two notations interchangeably. Okay. So I bring down 20, multiply by 1,000 to 0 and 3 zeros. I subtract 1 from the power, and I get 19, and multiplied by the inner function prime. When I differentiate the inner function, I get 1 over 4. When you differentiate R, you get 1, but 1 times 1 over 4 is 1 over 4. Of course, I will simplify 20,000 by 4, and I get 5,000, and then 1 plus R over 4 to the 19th power. That's the rate of change. Any other important information here, or other derivatives that you would like to work on, or we can look at the last section of this chapter, which deals with higher order derivatives. So we're going to practice in this section pretty much the same thing. Any questions? Say it again. 173, 172, 173. So, still from this or from higher order derivatives?
The last one.
Oh, the last, we are on page, that 1.7 is on page, I was looking at page 164.
Does the D mean differentiate?
Say it again.
Does the D, like before the A and R, the A divided by R, does that mean differentiate?
It means the derivative. Okay, this is a different. It's the same thing, but it's a different notation. We're going to talk about this notation later. So what does this mean is the derivative of A, function A, with respect to R, which means A is a function of R. The derivative of A with respect to R. First derivative, if you'd like to be specific. Thank you. Do we need more examples, or we move on? I'm assuming that you asked about the page number, so you can, should I wait for another second, or?
It's fine, thank you.
Thank you. Okay, so we can go back to it. Last section, higher order derivatives. Okay, here's an example. If we're given the distance formula, let's say S of t, distance with respect to time, the velocity, which is the rate of change of distance with respect to time, which is v of t, will be the first derivative of time with respect to time, the first derivative of the distance with respect to time. But the acceleration, which is a of t, is the first derivative of the velocity, but at the same time is the second derivative of the distance. And when we talk about higher order derivatives, we are talking about the second, the third, the fourth, the fifth derivative. Okay, so all we have to do is just work through problems using the same rules. Okay, on page 172. Of course, we have also the Leibniz notation that I used here. Let me use it again. So y prime or f prime can be denoted also by df over dx. It can be denoted by d over dx of y, or same thing, equals d over dx of f. They're all the same. But what about the second derivative? How do we signify with this kind of notation? It's called, as I said, Leibniz notation. It's d2f over dx2. Why? Why is that twisted? Because it's the first derivative of the first derivative. So we are differentiating the first derivative with respect to x the second time. So d2f over dx2. What about the third derivative? Will be d3f over dx3. And so on and so forth. So feel free to choose. I'm going to start with, I would like to look at 20 on 172. And that is f of x equals x to the third plus 2x, everything to the sixth power. And they want us to determine the second derivative. Find the second derivative. I cannot find the second derivative before I find the first derivative. It's not possible. So let's find the first derivative of this function using the power rule and the chain rule. So f prime, or dy over dx, or df over dx, all of them are the same thing. I bring down 6, I subtract 1 from the power, and I multiply by the inner function prime, which is 3x squared plus 2. And this is when it gets messy. Why? Because now I have a product of two functions. So when I differentiate again to find the second derivative of this function, I have to use the chain rule, but also the product rule. And of course, 6 will be patiently waiting. I'm not going to involve 6 anywhere. Well, it has to wait till the end. The first function prime, 5, x to the third plus 2x to the fourth power times the inner function prime, which is 3x squared plus 2, times the second function, I just want to put square because they are the same, plus, I copy the first function, which is x cubed plus 2x to the fifth, and I multiply by the inner function prime, by the second function prime, which is 3x. So let's stop for a second and see if this is okay. I left 6 outside. It can wait patiently. Don't care. 5, the function to the fourth, times the inner function prime, which is 3x squared plus 2. But I already have another 3x squared plus 2. That's why I already put power 2. Plus, now I copy the first function, but I differentiate the second one. I realize that I can factor out something from this term and this term. They have a common factor, and that will be x cubed plus 2x to the fourth power. So 6 is outside, and so is x cubed plus 2x to the 4th power. And let's see what is left. 5 is left. This is completely out. I still have 3x squared plus 2 squared. 5, I had 5, but I took out 4, and 6x. So plus 6x, and I still have left an x cubed plus 2x. So let's recap for 1 second. I realized that these two terms have x cubed plus 2x to the 4th in common. I took it outside next to 6. 5 is still left. I had 4 of those, but I took them out. And I still have 3x squared plus 2 squared. I reach the plus. I copy it. I reach 6x. I copy it. From these 5, I removed and I put in front 4 of those, so I still have 1 of them left inside. Now, I have to continue. I have x cubed plus 2x to the 4th power. And can anyone give us this and how many terms? And then I'll multiply it by 5 in a moment. How many terms we get when we square 3x squared plus 2? Can anyone give us 3x squared plus 2? Squared. 3x squared plus 2 squared. Anyone? Well, the first term squared is 9x to the 4th plus the product, which is 6x squared times 2 is 12x squared, and plus 4. That's why I show this every class. A binomial squared is 3 terms. Plus, I distribute 6x to these 2 terms, so I have 6x to the 4th plus 12x squared. Okay, now combine like terms. Keep those outside. And let's see what we get. 45 x to the 4th. 45x to the 4th plus 6. 51 x to the 4th. 5 times 12 is 60. 60x squared plus 12x squared is 72x squared. And 5 times 4 is 20. And this is it. I cannot factor out anything. And this is final. And this is the second derivative of the given function. Let's look at a velocity acceleration situation, like 48 on 172, where we are given s of t equals t squared minus 1/2 t and plus 3. S is measured in meters, and t is in seconds. Find each of the following. So we want to find v of t. No problem. Bring down 2 and subtract 1 from the power and differentiate this, and this is negative 1/2. Differentiate 3 and get 0. Then we are asked to find the acceleration. I'm going to differentiate the velocity and just get 2. The velocity and acceleration when t equals 1. So v of 1 will be 2 minus 1/2, which is 3/2, and the measurement unit is meters per second. but the acceleration, no matter what I plug in, it's still 2. So a of 1 is 2, and this is meters per second squared. Because it's a rate of change of velocity with respect to time.